It's nice, warm, a little hotter than normal. I think it's going to be 97 today in South Carolina. We're at the Liveline Training Center here. And ECAUS, a couple announcements. We are up to over 9,000 members now registered nationwide. Electric cooperatives, municipalities, contractors, IOUs. We got big, small, everything in between. We have some lineman training colleges. We have some schools out there that are grabbing a hold of these. I mean, this is just amazing what you guys are doing, what everybody's doing. And the Institute for Safety and Powerline Construction, they support ECAUS tremendously. They are bringing to the table, like Mr. Mark, they're bringing about 5 speakers in every single year for you guys, and they're paying for it. So get involved with ISPC, get involved with their nonprofit organization, and get their information, the resource that they provide. It's really important, and it's nonprofit, so you can't beat that. But real quick, we got Mark Forrester in today. As you all know, tomorrow will be Miss Emily Wilkins. She's with Austin Energy. She's the safety director there with Austin Energy, and she'll be speaking tomorrow on bridging the gap in training between apprentice and experienced line workers. So I'm excited. She'll be our first female certified utility safety professional to speak. And I've known her for about 2 years now. Great lady, and she's coming in today for you guys tomorrow. And then next month we got Mr. Jimmy Vaughn again with ISPC. He's going to be speaking on alternative use of heavy equipment, man lifts, forklifts in regards to OSHA. And then after that, Miss Jen Miller, she'll be coming in with OneSpan Powerline services. So she's going to talk about life on the wire with using helicopters. So that's going to be really unique as well. And Mr. Jimmy Vaughn is going to bring another different cog in the wheel as far as what we do here. So with that, I want to hand over the reins over to Mr. Mark, and he's going to go from here. Okay? Appreciate it, Mark.
Thanks, Brent.
Thank you, sir.
All right, good morning, everyone. Thanks for tuning in to today's ECAUS episode. So today, like Brent said, we're going to be talking about the substation craft, something I think is very important in our industry and sometimes doesn't get enough attention. So craft, what's a craft, right? Everyone in our industry is a craft person, right? So we're all skilled, we're all trained in special skills that we use, whether we're a substation electrician, whether we're a lineman, underground electrician, relay test person, doesn't matter. We all have a special skill, and we receive training and go through training to become that craft person in whatever facet of the electric utility industry we work in, okay? Today, like Brent said, we're going to talk about the substation craft, very near and dear to my heart. Basically spent my entire career in the substations, and again, it's a very important part. Nothing in our industry works without the substation, right? Customers don't have power coming to their house unless we go through substations. So very important part of the makeup of the electric utility industry, okay? A couple statistics I wanted to share with you, doing a little research, preparing for this. As you can see here, over the next 10 years, we're going to need to hire about 80,000 electricians a year to keep up with the demand, okay? With the transformation that we're looking to do into more renewables, those types of things, we are going to need to hire a lot of people, okay? Another one I thought was interesting, only 2% of electricians are women. So I found that very interesting, why, you know, it's a trade. I personally know some women that are in the electric utility industry. Companies I work for, we've had lineman women, very skilled, very capable, and so, you know, something I think we need to get, and ECAUS will help with that, but to get the word out to people, right, that our industry is more than just for us guys, right? Obviously, we're facing a massive labor shortage, right? So 80,000 people a year is a large task to overcome to be able to support this industry over the next number of years. Okay, so just some things I wanted to share with you there. So let's dive into the substation world. So we're going to talk about a couple things today. We're going to talk about what substation workers do. We're going to talk about what they need to know, some of the training and expertise that they need to know. We're going to talk about substations, what's in a sub, what does a sub do? And then I'm going to finish up at the end of the presentation on safety in substations, right? So that's really what ECOS is about, you know, safety in our industry, and so we'll end, you know, on a high note there. So what do substation workers do? You can see here, installation construction, right? So this would be new substations, additions to substations, those type of things. Can be anything. You know, one day we could be installing steel structures, the next day we could be pulling cables in trenches, the next day we could be inside doing control wiring in panels. We could be installing other equipment inside the substation yard. So a very vast array of work that these guys need to be able to know and be competent in. So quite the challenge. And then not to mention, you know, this picture shows outside open air. We also have gas insulated bus and things like that that get installed inside. So a really vast array of equipment that these individuals need to be skilled on and competent in working on, okay? Maintenance and repair. This is probably what most people think about when they think of substation electricians, right? Substation's up and running, it's in service, and what do we do to maintain that substation, right? So, you know, we're doing inspections on a regular basis. That could be weekly, monthly, quarterly, whatever the case may be. We proactively take equipment out of service, perform cleaning, lubrication, testing. We could be doing timing tests on circuit breakers. We could be doing oil testing on power transformers. It could be equipment that has been found to be faulty, right? Through maybe infrared inspections, found hot spots, things of that nature that we need to take that equipment out of service and fix it, okay? So maintenance is a big aspect of the substation workers' daily tasks, okay? Troubleshooting, okay? Sounds easy. Okay, hey, we got a problem, right? We go out, let's figure out what's going wrong or what happened, get the problem resolved, and get the substation back in normal service. Not as easy as it sounds. I'm going to show you in a little bit some of the equipment that these guys work on. Again, they need to be very skilled. They need to understand the system they're working on, right? It's kind of hard to troubleshoot things and fix things if you don't understand how it operates. And so troubleshooting and diagnostics are a very important part of what they do in the substation world. Okay. Upgrades and modifications. So, you know, as we go through time, technology gets better, equipment ages. So a lot of what we do as well, and we've been over the last 8-10 years have been in a big upgrade boom in the electric utility industry, right? Upgrading our facilities, preparing for this renewable and electric evolution that we're going through. And so upgrading our substations to be able to provide that reliable power to our system is key to that effort. And so we could be, again, upgrading because of growth. We could be upgrading just because equipment's old. There could be new technology out there when it comes to monitoring, relaying, those type of things where we need to go in our substations and upgrade our equipment so that it can handle the new technology. So upgrades and modifications. All right, so we talked a little bit about what we do in the substations. Now let's talk a little bit about what these guys need, guys and gals, craft people, need to know in the substation world. So number one, technical expertise, right? So you have to have a strong foundation of electrical theory, okay? Very complex systems within our substations. And again, like I mentioned earlier, we need to know what it is and how it works, right? If we don't understand how the system works, how can we fix it? How can we maintain it, right? We need to understand, again, electrical theory, both AC and DC. We need to be able to interpret diagrams, prints, things of that nature that correspond with the actual equipment in our substations, okay? Some other things we need to know too, like I said, we also deal with switchgear, right? Whole different animal than open air equipment out in a yard. Protective relaying, right? A lot of electricians, substation electricians get into relaying. So we need to understand not only the power side of it, but the relay side of it. So again, a very vast array of equipment and systems that these people need to be competent on, okay? We talked about AC. I also mentioned DC theory. So, you know, the substation battery here, you can see a picture of this is actually a 500 kV substation DC battery. It's basically the heartbeat of the substation. The DC battery doesn't do a whole lot under normal conditions. You can see in the left of the picture there's some battery chargers. There's a primary and a backup that provide the DC power to the station under normal conditions. Also provides a charge to the DC batteries so that they're prepared should we have a power outage. That's when the DC battery comes into play. So we lose our AC power to the station. These DC batteries will allow operation of equipment, most normally tripping, right? So if AC power goes out, all your equipment's going to be in the status it was when the power went out. So obviously when we go to bring that station back online, we do not want all that equipment to be already closed, and essentially you're going to energize a line into that station and pick up the entire load of the station. So the DC battery will allow us to open those breakers up. This battery here gives about a 16-hour window of opportunity or support to this station without having a charge to it. So we need to understand the DC side of things as well, okay? Safety awareness, right? Big part of everything that anybody in the electric industry, or any industry for that matter, needs to be aware of, right? This is where we, if not done properly, we get people hurt, right? Things go wrong. So we need to be vigilant about our safety awareness. Now, there is, you know, there's equipment here. You can see PPE, tools, tags, that we need to use to keep ourselves safe in the substation world. When we're working energized inside a control house on control equipment, we need to use insulated tools. When we're working, I mentioned switchgear and metal-clad switchgear, that type of stuff. And also some of the things in our open air substations require us to go above and beyond our normal FR PPE. So we have category 40, Cal 40 Cal gear that we may have to put on because of the incident energy that could be there should something go wrong when we're switching on that equipment. The other thing with safety awareness, and I'll share some statistics with you when we get to the safety section, but very important that we as individuals own our own safety, right? It's very important to have our safety professionals. They're kind of our guiding light, driving the ship, the captain of the ship. But if us as workers do not do our part for safety, we're never going to get to a point where we stop hurting people, okay? All right, problem-solving skills, okay? So we talked about technical expertise. One of the biggest things when troubleshooting is problem-solving, right? Again, we need to understand the equipment. We need to be able to interpret prints and relate those prints to the equipment that we're working on. We need to have the ability to analyze and diagnose what is happening or not happening with that piece of equipment, right? Sounds fairly easy, but a lot of times what happens is these substation electricians will be troubleshooting and they're not trusting their process. They're not trusting their meters, right? And so what tends to happen is they get going down a rabbit trail, right? And they get further away from the problem instead of trying to solve the problem. So very important part of troubleshooting is you have to develop a process that you as an individual is comfortable with. You trust it, it works for you. It may not be the same as your coworker or somebody else, right? They may have a different method for troubleshooting, but you need to understand your method. And then you need to trust your equipment, right? You need to know when that meter says 120 volts, or it says 0 volts, or it says 150 ohms, or whatever the case may be, whatever you're testing and troubleshooting, you need to know if what that meter says, is it good or is it bad, right? What's the expected result when you put those test leads across a circuit? So very important to understand that process and trust your process. Just some other things that substation workers need to know, and these really apply to any job in our industry or any industry for that matter. Attention to detail. The one big one I do want to point out is continuous learning, because I think it's a gap in our industry, not only in the substation field, but in every field, right? Everybody has probably worked for that company where you become a journeyman electrician, a journeyman lineman, whatever the case may be, and okay, you're good, fly away, we'll see you at retirement, right? Well, it's not good enough, right? We're doing our people, our employees, a disservice by not giving them continuous learning. We got to continue to teach our people and allow them to learn these new technologies, right? A lot of times, especially in the utility industry where I came from, especially nowadays with diminishing workforce, contractors install a lot of this new equipment, and then it gets turned over to the house utility. Here you go, it's yours, maintain it for the next 20 or 25 years. Well, if we're not teaching our people that new technology, we're setting them up for failure, right? We need to be showing these people this new equipment, teaching them how it works, how to troubleshoot it, what are some of the potential problem areas, so that when they get called out or have to go respond to an issue with this equipment, they're comfortable and confident that they can determine what the problem is, okay? A couple other ones, teamwork, communication, right? We got to have clear communication. A lot of times in the substation, we're working with more than just ourselves. We may be working with relay test folks. We may be working with engineers. We may be working, obviously, with our own, teammates. But we got to have clear communication. We got to be talking to each other, discussing what we're working on. If we're taking equipment out of service, we got to be clear with each other where our zone of protection is and where our blocking is and such. Couple other ones, organization, that goes back to the troubleshooting portion of it. You have to have an organized process to do troubleshooting and your work, right? And it's no different than any other trade as well. And then adaptability and flexibility, right? So, coming from the utility industry, I was a supervisor at one time before I came into training. You have to be flexible and adaptable, right? You plan your day, you send your guys out, they're going to do their work for the day. They get to a station, switch things out, get things ready to work, and then the phone call comes. Hey, something just broke, or something's out of power, or whatever the case may be. And you got to call those guys and say, hey, I need you to stop. I need you to go here. We got a problem, right? Very frustrating to the worker, right? They have their mind set on what they're doing for that day, and then all of a sudden you pull the rug out under their feet, right? And so you have to, as a worker, be able to tune that stuff out and not worry about that and focus on the next task at hand, right? So you could be going from a very easy, hey, today I'm going to service a piece of equipment, to now I'm thrown into a troubleshooting scenario where I got to go somewhere else, figure out what's going on or what's not working, troubleshoot it and fix it, right? So whole different mindset, whole different set of hazards that we got to now turn our mind to and focus on that new task at hand. Not to mention it just threw your day up in the air, right? Maybe you had plans to go away after work or something, go to your kid's baseball game, right? And now you're like, well, not sure I'm making it. So missed many a family picnics and holidays and all that stuff. So you got to be, in our industry as a whole, not just in the substation world, we got to be very flexible. Okay? So let's look at what's in a substation. So I got about a 2-minute video here or so that's just going to scroll through some of the equipment that substation electricians need to understand and be comfortable working on. All right, so as you can see, quite the mixture of equipment that these substation craft people need to be able to work on, be familiar with. Vast array of different voltage levels, size equipment, from the power side to the control side. Just a lot of stuff that these guys got to be competent and be comfortable working on, okay? So let's turn to what is a substation, right? What's a substation do? Everybody sees them out there. It's that nice little square fenced-in area that you'll see driving through your communities. Main purpose of a substation is to transform voltage. Most cases, it's to take a higher voltage and step it down to a lower voltage for distribution throughout our communities, right? If you step back to the generating side of things, back into your generating plants, there we deal with step-up voltage, right? So it comes out of that generating facility at a lower voltage and goes through a step-up power transformer to get it up to the transmission level that we can send bulk power across our grid and be able to get it out to those distribution stations at a higher voltage, right, before we step it back down into the distribution world and get it out to our customers, okay? This is a distribution sub here. You can see if you look straight ahead there, we call it a bus section. There's actually two bus sections, one on the right, one on the left. So you can see on the left of the picture, we got the transmission power coming into that air brake structure. In this case, it's 69 kV. Goes through a power transformer, step down, takes it from 69 to 12 kV, distributes it out to the bus sections inside the substation, which in turn then is distributed into, you can see this particular one has 4 circuit breakers there in the background, which will then feed your power out into your distribution network, either via underground or overhead distribution lines. And then obviously that runs through our communities and feeds our businesses and customers, okay? Also, substation, we use substations for switching operations, right? And this can be for a various number of reasons. Here on the screen, you see a one-line diagram of the sub we just looked at on the previous slide. And so we can use these substations to reroute power. It could be because of faults. So we need to isolate equipment to be able to work on it or replace it, so we can not only reroute power within the substation, but we also have field ties and things that we can do out in the distribution network to be able to reroute power and keep the lights on for everybody while we fix faulty equipment. We also have the ability inside the sub, we need to proactively maintain this equipment, so we have the ability to be able to reroute power within the substation and take equipment out of service so that we can maintain it. All the while, nobody ever knows the difference that we're even doing anything. The lights stay on. We can do that through switching operations within inside the substation here. Okay. Just continuing switching operations, you can see these are some 12 kV disconnects within a substation that we will use to be able to close or open to be able to reroute power so that we can maintain our system reliably, keep the lights on for everybody while we do what we need to do, whether it's just moving power around. Maybe we have an overloaded circuit and we need to distribute some things and change some flow of electricity throughout the substation to be able to maintain a good, reliable system. Okay. Protection and control. So, inside the sub, obviously all this equipment has the ability to detect faults, overloads, abnormal conditions, and react accordingly, right? And so, this is a 12 kV circuit breaker. Again, goes out into our distribution network. We'll go through some other protection and control equipment, right? Vipers, OCRs, power fuses, those type of things. And these are all coordinated to isolate problems on our system that will maintain as small of outage as possible when outages do occur, right? And also to prevent further damage to our equipment, right? So the last thing that we'll talk about inside, or what is a sub, is metering and monitoring, right? So not only does equipment like circuit breakers will open and trip for faults and things of that nature, but those are monitored by metering and relaying, okay? So we're looking at currents, we're looking at faults, right? Ground, phase to ground, phase to phase. We're looking at things like power factor and stuff like that, bus voltages, line current, things of that nature. And these relays monitor the health of our system, right? So again, they will tell this equipment when to isolate a fault, when to trip. It'll also send status to our system operating office, right? So that people can understand, hey, if I see a current getting high, it'll go to an alarm level, it'll send an alarm to our operators, and they know, hey, we have a problem developing here, right? So hopefully we can deal with that problem before it gets to a point of tripping equipment offline. All our equipment, not only in the sub, but even out on the lines, has some sort of monitoring and metering that can tell us when things are about to go south. Okay. All right, so now I want to turn to the safety side of things. Couple more statistics here I just thought were fairly interesting when it comes to safety. This slide deals with the entire industry as a whole, and then the next slide is just specific to the electric utility industry. But you can see here, and this is again from the Bureau of Labor and Statistics, 2021, we had a little over 5,000 fatalities, okay? In 2020, we had just under 5,000, right? So we're kind of stagnated right there at a plateau, if you will. You can see the incident rates there per 100,000 FTEs. Since 2019, we're right around 3.5, right? So 3.5 fatalities per 100,000 full-time equivalent workers, okay? So, and if you look back, that trend has been there for the last number of years, okay? When you dive down just into the electric utility industry, you can see here, took about 2 decades or a little more to have this number, right? Over the last 20, 30 years, we have obviously significantly increased our focus on safety and have decreased our injuries and fatalities. But you can see here that over the last decade, we're stagnant, right around on average 150 fatalities per year just in our industry. So while we have, you can see here, more than halved our percentage from 1980 to 2020, there's still 150 of our brothers and sisters that aren't going home every day because something happened, right? Whether it was to their, a fault of theirs, or whether it was something that happened on the system. But movements like ECOS is where we need to tackle the rest of this 150 persons, okay? Again, like I said earlier, we need our safety folks, we need our safety professionals, right? They're putting the programs in place and monitoring these statistics and sharing this information and kind of directing where we go in safety. But the bottom line is, unless you as an individual take safety as a value, right, and make it a part of everything you do, we're not going to move this number, right? We need every individual to feel that they're their own safety professional, right? Buy into it, you know. And then once you do that for yourself, then you can help out your brothers and sisters on your team and make sure you're helping to keep them accountable and safe as well. But number one, you got to do it for yourself, okay? All right, so substation safety. You can see here OSHA regulation around substation fences, that they shall be grounded. OSHA tells us all our substation fences shall be grounded, right? And when we remove a section, expand a fence, reduce a fence, whatever the case may be, we need to ground or bond as necessary to keep that protection for our people, to eliminate differences in electrical potential, okay? You can see in the top picture there a picture of a substation gate, right? So, you know, a lot of people, and I know this just because, again, I worked for a utility, I was in this industry, I had people work for me as a supervisor. I've watched countless people pull up to a substation and just go up and stick the key in the lock, unlock it, throw the gate open and go in the sub. Well, if, for by chance, those fence grounds, or you can see in the bottom left picture there, the bond between the substation fence and the gate, if those are compromised, when you open that substation gate, you're creating a difference of potential between those two fence panels. And so, you know, at our smaller distribution subs, probably not that big of a concern, but you know, you still got to be aware of it. But as you get up into our higher voltage transmission stations, where we have to worry about induced voltage much more, this could become a tremendous hazard that you need to recognize, right? You need to be looking for these things. You know, I know we train for it when we go through our substation apprenticeship, you know, letting our people know, listen, the first thing you got to do when you pull up to these things, right? They could sit there for months and nobody's ever been there. You need to be very vigilant and aware of your surroundings and make sure you're checking this stuff before you walk into a substation or go through the fence or gate, okay? So substation ground grid, 2 purposes for the ground grid, right? So, you know, very important part of the substation system, okay? This ground grid is just what it says. It's a grid. You can see the picture there of the ground lines on the ground. It's set up in a grid configuration like this. And then all the equipment within the sub is bonded to that substation grid. And basically it creates an equipotential zone between the substation floor and the equipment so that when you walk up and lean against a structure or touch a structure, you're not susceptible to touch potential. okay? So the second thing obviously it does is it eliminates those hazards. So again, once we're inside the substation fence and going to do whatever we're there to do, inspection, switching, work, whatever the case may be, we need to be vigilant that we're checking the connections from the grid to our equipment, right? You can see these in a couple of these pictures, the substation ground tails that come up to the structures look to be blue. Well, they are blue. It was a utility's way of trying to prevent theft. This utility went through probably about 5 or 6 years ago, went through, when the price of metals were up, went through an array of substation thefts where people would break into our subs and cut these ground tails, right? And they'd eliminate them and they'd go to try to turn them in for scrap. So the local authorities worked with the utilities in that area and maybe have done this around the country, but they worked with the scrap dealers and they worked with the local authorities and with the utilities to say, listen, if somebody comes to you with a load of scrap copper and it's painted blue, it's stolen, right? It's not something that they got on their own. So, you know, these ground tails, some of those pictures you saw in what's in a substation from the 500 kV yard, I have personally taken an amp clamp and measured 47 amps on that ground pigtail, right? So not only are they eliminating a current carrying path, you know, if the conditions happen to be right when they cut these things, they're going to get potentially dead, right? So very important to make sure these connections are intact when you're working inside a substation, okay? Here you see a picture of a ground mat. We use these not only in the subs, we use them out in the T&D world as well. This is at the base of a gang-operated disconnect, so you can see the handle there at the top of the picture. Operates a gang-operated disconnect at the top of the structure. And these ground mats are placed. You can see there's a ground tail to the structure that's also connected to the ground mat and connected to the substation ground grid. And this mats are placed wherever you may be operating equipment that could potentially become energized if something goes wrong, right? And what it does is put you at an equal plane with everything in that area, right? So if something does go wrong, your best course of action, unless there's debris falling from the air, is to stay on that substation mat. Then you're at an equal potential. If you hop off that mat and run, you're going to be susceptible to step potential, right? Everybody's heard the adage about you throw the rock in the water and the ripples go out. Well, it's the same thing with step potential. You know, so if you leave this mat in an incident, you could be susceptible to step potential. Okay. All right, so another OSHA regulation, equipotential zone. So this is a big one for me, and I'm going to share a story with you here in a little bit about a friend of mine back in 2008 that darn near lost his life. And it was all around equipotential. And the thing that I have kind of made my goal over the last year or two is to make people aware that equipotential zones, work zones, apply to the substations just as they do to the T&D world, right? If you look at OSHA and things of that nature, all the examples are around poles and structures. There's no examples in OSHA's regulations around substations, right? And equipotentially grounding and bonding in substations, but it applies all the same, okay? And especially as you get up in voltage levels, right? We get into those 230 kV, 500, 765, so on. The induced voltage possibilities in those scenarios are so great that we need to be equipotentially grounding and bonding ourselves into our protected work zone. And if we're not, it's only going to be a matter of time, and you're going to be one of those statistics, okay? So let's talk a little about grounding and bonding. So I want to share, first I'm going to share 3 safety principles with you. Most of you may have seen these. This is nothing new. but I feel it's important enough that we discuss it as much as we can. So safety principle number 1, current flows in every available path, right? And inversely proportional to the resistance in that path, right? If you, as the worker, are one of those paths, you're going to see current. Should there be an induced voltage or a fault or a switching error, something of that nature, one of these current paths, lots, most, little, or less, is going to be you if you don't have yourself properly bonded and grounded into your work zone, okay? Safety principle number 2, if you insert a resistance into a current carrying grounded conductor, a voltage rise will appear, okay? So you can see at the top there, we have an open point, 7,200 volts. Put a meter across that, it's open, no resistance, you're gonna measure 7,200 volts to ground, right? In the second depiction there, you can see you're gonna have something less than 7,200 volts, right? We've inserted a resistance in that, whether that's a dirty connection, whether that's a not properly closed disconnect, whether that's you, right? That resistance in there could be you, okay? There's going to be a voltage rise across that resistance. And then obviously the last one there depicts you as the resistance, and if you bond or ground across that open point or resistance, right, that voltage goes to 0, right? Because that jumper or that bond across that resistance or open point is less resistance than you are. So, right, it's gonna, more current's gonna follow that path, okay? Safety principle number 3, takes 50 volts to break the resistance of your skin. 50 volts, okay? Pretty much everything we work on is greater than 50 volts, other than maybe our DC systems, and even those, the one I showed you earlier was 130 volt DC, but 50 volts to break the resistance of your skin. On the left side there, you can see, some of you may be familiar with this chart. This is dealing with current, right? And you can see in about the 4th row down there, 6 milliamps to 16 milliamps is often referred to as the let go range, where you could potentially not be able to let go of that conductor. So 50 volts and as low as 6 milliamps, right? Doesn't take much. The very next row, 17 to 99 milliamps, could, depending on conditions, result in as much as death, okay? So this is how little of voltage and current it takes to mess with the human body, right? So we need to be protecting against this, okay, in everything we do. So, grounding. And this is, at least in my experience, this is a very, very misleading phrase. Very misleading, right? Grounding for the protection of personnel. We're not grounding for the protection of personnel, okay? Grounding does not assure that a worker is not going to get shocked or electrocuted, okay? The number one purpose for grounding is to trip, okay? Should something happen, should something become accidentally energized, a fault on the system, a switching error maybe, our grounding is meant to isolate that fault as quickly as possible, right? To minimize what you as the worker in that work zone see to your personal self. But it doesn't mean you're not going to see anything. And I've had too many people in the substation, including people that work for me, say to me, well, I'm working in a substation and I have half of it out of service and I have my sources of potential energy grounded, right? My high side coming in, my low side going out, I have those potential sources grounded. I'm good. No, you're not good. I'm here to tell you you're not good, right? Especially as we get up in the higher voltage substations where induced voltage comes into play, okay? Grounding, when we apply grounding, it collapses the voltage, right? Makes the system seem safe, okay? Everything's good, we're grounded, right? Everything's intact, we're good. The problem is that temporary grounding that you just applied for your protection can develop its own potential. Okay? It can complete the path. You're still good at that point until you go to disconnect something. Okay? And then you break that path and you become that inserted resistance of that current carrying grounded conductor. Okay? So, according to OSHA and ANSI and IEEE, grounding for the purpose of protecting employees, right? So, a couple OSHA rules here, 269N43, protective grounds shall have an impedance low enough that they do not delay the operation of protective devices, right? We just said grounding is for operating our protective relays and isolating the problem as quick as possible, right? 269N3, our grounds need to be arranged to prevent each employee from being exposed to hazardous differences in potential, right? Grounding, bonding. We need to differentiate, especially in the substation world. I think the line world and so on does a really good job of equipotential grounding. It's really been kind of rolled out that way in the industry, right? You know, we have our information and such, like I said before, is all geared towards the T&D world, right? The line world when it comes to equipotential grounding. In the substation, not so much, right? And so we need to understand as substation workers, when we ground equipment in a substation, we're not 100% protected. We need to go that extra step, okay? When it comes to personal protective grounding, what's the difference between induction risks and unintentional energization? There is no difference. They're both AC voltage, okay? They both will hurt you just the same if you get into the conditions where you become part of that current carrying path, okay? So I'm going to end this. I have a little story I want to share with you. I mentioned it a little earlier. So this was early on in my career. Matter of fact, I was still a trainee at the point when this happened. You see a picture here of a wave trap installed on a downcomer in a 500 kV substation. Looks fairly innocent, right? The job for this day back in 2008 was to replace this wave trap. We were upgrading to a new wave trap, and so the job for that day was to switch out a service, establish a protective work zone, apply grounding, apply bonding, and go up and replace this wave trap. So we're working with a foreign utility. Okay, the 500 kV line that left this station went to another utility. Okay, it ended up, so we start the process probably about 8 o'clock that morning, and then things stall. Okay, there's a 4-man crew working this job. Okay, one of those individuals was a trainee, one was a journeyman electrician, the other 2 were electrician leaders. All right. Ended up at the end of the day, it was about 2:20 in the afternoon till we finally got our permit applied to this work zone. By that time, the trainee had left, okay, and headed back to his normal area for his quit time at 3:30. And so the 3 elder, I shouldn't say elder, the 3 more experienced gentlemen were there, and this is when things started to take a turn, right? And so we always talk about, you know, nothing's that important that we got to take shortcuts, right? Nothing's that important that we need to hurry or rush or be pressured by time, right? And in this case, there was no time pressure, right? There's no customers out of service. You know, this is one of those routine jobs where we were able to isolate it in the system, affect no customers, no power flow, anything. When the crew finally got their permit at 2:20, the next step after and we call them permits where this happened. I know a lot of people call them clearances, same thing, right? So the clearance holder, the permit holder, accepted that permit from the system operator, and then was issued at our 500 kV yards. There's actually gang-operated ground switches that go closed to protect our work zone. The key about those ground switches are, again, the conversation we just had, they are for tripping. They're not for personal protection. And so this 3-man crew that was left at the end of the day decided that they needed to get something done that day, right? Instead of taking a stop time out and saying, listen guys, let's talk about this, let's think about it. We just had an evolution in isolating our equipment that took way longer than expected, right? And some guys were frustrated that we didn't get to do this job today. Worst case, it bleeds over into tomorrow. We come back tomorrow morning fresh and we go at this job and make it happen, right? But these 3 individuals, 90 plus years experience in the substation world, 90 plus years experience. All of them had been there over 30 years working in the substation world. So they decide, okay, we have our permit, we have grounds closed at this station, we have grounds closed at the foreign utility station. I'm working between grounds. Remember I said a little bit earlier, hey, I have my high side, my low side isolated. In this case, same voltage, but I have both my sides isolated and grounded, right? So 2 of these 3 gentlemen get in a 60-foot JLG man lift, go up in the air, okay? You can see there's a set of parallel bypass leads that come around that wave trap. Remove those, okay? The last thing they wanted to do for the day was take off that piece of 4-inch bus that goes from the wave trap to the bus work below. And they wanted to take those other 2 leads coming off the bottom side of that wave trap off, so that all was left was that piece of 4-inch bus holding the wave trap. So that the next morning they could come in, put the boom truck up in the air, hook up the wave trap, lower it to the ground, lift the new one up and put it in place. So they go up, they start to take things apart, you know, kind of in a hurry because we're nearing the end of the day. They take the bypass parallel leads off, they take the piece of bus out, they take 1 out of the 2 leads from the bottom of the wave trap, and the very last thing, or the next to last thing they did was remove the cable to paddle flat connection at the bottom of the wave trap from the second lead, the last lead that was remaining. Well, as you can see, or as you can imagine, right now that's their ground path, right? Their grounds, they have put up no temporary safety grounds to bypass around this open point they're about to make in this circuit, okay? They have in their mind the whole time, I'm grounded, I'm good. Well, one guy in the man lift holding that lead, second guy in the man lift operating the impact gun to remove the nuts and bolts from that paddle connection. He removes the last nut and bolt from the paddle connection, and when he does so, the journeyman electrician holding that cable to flat connection pulls it away, other hand on the rail of the man lift, and he just became the path to ground, okay? Not sure how he's not dead. Seems, I'd probably want to say 15 to 20 seconds. At a minimum, he was exposed to that induced voltage. The only thing that saved his life, I believe, is 1, the man lift was not grounded. So another fallacy working in our stations, right? Hey, I'm on rubber tires. I don't have to ground, right? I'm isolated. Wrong. Now, in this case, because they didn't have the proper bonding and equipotential grounding in place, that might have saved his life. I don't know that for a fact. That's just an assumption. But luckily, the quick thinking of the guy on the ground to go over to the ground controls on that man lift, flip it to lower controls, and just literally drop the basket out of the air. Broke the connection between the induced voltage and this employee. Don't know how it happened. The second gentleman in the basket did nothing but freeze and duck down. He knew he had enough wherewithal to know that if I touch this guy, I'm going to be the second casualty, right? Whether that's injury or potential fatality. The bottom line is we cannot rely on grounding alone, right? We need to establish these equipotential zones in our work zones in the substations, right? Everything in there is metallic, right? All the structures are grounded, right? What's voltage trying to do? Trying to find its path to ground, right? And like I said earlier with safety principle number 1, you know, the current's going to go wherever it can. And in this case, it went through him. Luckily, he was not killed. He today has this arm just below the elbow, and he has this on his left hand. Okay? This gentleman was 6.5 months from retiring. Talked about it all the time, right? Moving out west, gonna go fishing, gonna go this, do traveling. Changed his entire life in that split second because they decided they needed to get something done that day. Guys, we cannot rush through this work that we do, right? We cannot do it. We need to take our time. We need to be deliberate. We need to recognize these hazards, okay? We need to understand them. We need to understand when we're going to put ungrounded equipment or ourselves into a work zone that could potentially have hazardous differences of potential, right? This guy was very lucky, good friend of mine, ended up retiring, but basically spent half of his last 6 months till retirement in a burn center, okay? Surgery after surgery after surgery to remove dead skin and so on. So listen, not only did it change that guy's life forever, it changed his wife's life forever. It changed his family's life forever, right? We just cannot rush through this work. We need to be deliberate in everything we do. We need to recognize these hazards, and we need to keep ourselves safe. Like I said a little earlier, it's up to us, right? If you're out there and you're an individual that thinks, oh, it's the safety guy's job to protect me, unfortunately, down the line in your career, you may end up being one of the statistics, okay? This stuff has to come down to the worker level, and that's what ECOS is doing, right? We're getting this out. We're talking to the people actually doing the work, right? Sharing this stuff with them. You know, if you're a supervisor or you're a safety person that watches these things regularly and other stuff like this too. It's not just ECOS. There's, you know, but we need to be sharing this stuff with our people. We need to be getting the message out. We need to be letting people know that there's a right way to do things and there's not a right way to do things, right? So hope everybody got some good knowledge and some good information out of this presentation. Hopefully you understand, if you didn't before, hopefully you understand a little bit more about what goes on in the substation and what these people need to work on and understand and the hazards that they deal with on a regular basis. Thank you for attending today. That's all I have, Brent. So be safe out there, guys. It's a dangerous job we do.